Hello everyone, just some information on the upcoming test this Thursday. You'll have 16 problems to work through for 40 points. The first 6 questions are going to be a combination of true, false, multiple choice. And then the remaining 10 questions will be application problems, just as what you've been working with on your Chapter 6 study guide. So please let me know what questions you have over the Chapter 6 study guide. Part of today and tomorrow will still be to continue to work on that. But I do want to start Chapter 7 today. So chapter 7, like 6, only has 3 sections, and they're closely related. There's going to be some differences with them, depending on what we're asked to find. So this is truly the start of what we consider to be inferential statistics. So this whole chapter focuses on one topic called confidence intervals, and then we're also going to see how to calculate sample size. So section 7.1 has you find confidence intervals for the mean when the standard deviation is known. But what do we do if it's not known or unknown? Then we go to section 7.2, confidence intervals for the mean when our population standard deviation is unknown. And in section 7.3, confidence intervals and sample size for proportions. So we're just going to get started today on section 7.1. All right, so again, this is the start of us really diving into inferential statistics. These are just an estimation as we estimate the value of a parameter from information obtained from a sample. Remember, a parameter is a measurement that pertains to a population. So we're estimating the value, some kind of measure for a population from information obtained from a sample. So as I just mentioned, a statistic is a measurement for a sample, and a parameter is any kind of measurement. It could be the mean, the median, standard deviation, variance. That's dealing with the population. So we also have what's called a point estimate. This is a specific numerical value just like we're kind of pinpointing this value. So it's a specific numerical value estimate of a parameter. The best point estimate of the population mean is going to be the sample mean. I'm just going to abbreviate estimate here. So the best point estimate of mu, the population mean, is the sample mean, x bar. So the first example that's going to pertain to this is, let's say a college president wishes to estimate the average age of students attending classes this semester. Let's say he has a sample of 100 students. Let's say the sample mean, x bar, is 22.3 years. So this college president, he or she, could infer that the average age of all students attending classes this semester is 22.3 years. So we're just using a point estimate here. They have found out the sample mean, and then they could use it to be a good point estimate for the population mean. So what we just wrote out here, the sample mean is the best estimate of the population mean. We'll go back and use that same word again, but we'll pluralize it here. Sample means vary less than other statistics such as medians and modes. Now keep in mind what we were doing from the last section in chapter 6 when samples are selected from the same population. Let's take a closer look at estimators. So we just described a point estimator, but going back to the very beginning, remember statistics, measurements coming from samples, are used to estimate parameters. So statistics, again, are sample measures. And parameters are population measures. So we could use that in place. We could say sample measures are used to estimate population measures. A good estimator should be unbiased. So I'm not going to write all this out, but I will explain it. The expected value or the mean of estimates obtained from samples of a given size should equal the parameter being estimated. But all you have to really remember is a good estimator should be unbiased. It needs to also be consistent. As the sample size increases, the value of the estimator approaches the value of the parameter estimated. And that kind of makes sense. The larger the sample size, the closer we're getting to the size of the population, in a way. And then the third is relatively efficient. Of all the statistics to use the one with the smallest variance. But all you have to do is remember that a good estimator should be unbiased, consistent, and relatively efficient. So we looked at a point estimate of a parameter. Now let's take a look at an interval estimate. So this kind of gives us some wiggle room. If we have just an interval, let's say we're talking 0 to 10 versus saying it has to be a 5. That would be a point. If we're picking a number specifically and we like toss a coin, we have to land exactly on 5 versus we just have to land somewhere in between 0 and 10. So an interval estimate is going to be better, as we'll see throughout this chapter. So we're talking about an interval or a range. Of values used to estimate the parameter. A parameter is specified as being a value between two values. And you're going to see when we actually start to write a confidence interval. And two things are going to happen. Either the interval contains the parameter or it doesn't. we assign what we call a degree of confidence. So a degree of confidence can be assigned before an interval estimate is made. Actually, go one more page for today. All right, so the common confidence intervals are 90, 95%, or 99%. A confidence level is a probability. So it's the probability that the interval estimate will contain the parameter. Assuming a large number of samples selected and the estimation process are on the same parameter is repeated. All right, so tomorrow we will take a look at some formulas involved and how this applies to the standard normal distribution, and then we'll get into some examples. So what I want you guys to do, still just prepare for the test. Make sure that you are finishing, checking, and correcting and asking questions over the Chapter 6 study guide.